Hello everyone, welcome back to my course on discrete mathematics, and today we are going to deal with functions. Let's define what is a function and what are the different types of function. Well, you might have already studied about some basics on sets. Yes, function is an extension, version, something similar to set, but it's a little bit different. Let's define a function. A function takes an element from a set and maps it to a unique element in another set. So you can see there are two sets, and a function actually it takes an element from one set and maps it to the element in other set. So that's the function. As we go deep down into this function, you can also see how this terminology can also be used in programming terms. Well, in program terms, we also use functions, but this is a mathematical term here that we are going to use, and we are going to see how the functions can be mapped, how function helps elements to be mapped, as well as how a function actually performs various other manipulations. For example, in fact, you can have a function inside a function and so on. Let's begin with the terminologies. Let's say you have this two domain R and Z. Let's consider R as say real number and Z as integers, and a function actually maps the domain elements from this domain R into the domain Z. Say for example, here in the real domain you have 4.3, and that is mapped to the integer domain, that is 4. Here again, as I told you before, this is the real number domain, and onto your left is your real number domain, that is R. Onto your right is your integer number domain. So we call it as a codomain. So this 4.3 is the pre-image of 4, whereas 4 is the image of 4.3. It's as if simply looking at a mirror, you see your image. In a similar fashion, you're actually mapping this 4.3 to 4. Yes, F maps R to Z. Let's see more on functions. Here it comes like Alice is mapped to A, Bob is mapped to C, Chris is mapped to A, Dave is mapped to F, Emma is mapped to D. Yeah, a class grading function is given here. This names are domain and the grades are the codomain. Here is another example, or a string function is given to us. The string A is mapped to 1 and BB mapped to 2, CCC mapped to 4, D mapped to 2, E mapped to 1, and so on. This is another example here. Yes, this part A has the pre-image of 1, whereas 1 is the image of A. Let's see more on the function. There are some more functions here. So we call this place where it has been mapped in the codomain as the range. So we can also consider this function. For example, here DD is being mapped to 2 elements. So that is not allowed in a function. In other words, this is an invalid function. So that's more information that you have here. So generally speaking, whatever it has been mapped in the codomain we call is the range, and when you have the element in the domain that is mapped to more than one element in codomain, we would say it is not a valid function. It is not a function. So another one, again the domain, there is something missing there. As you can see, E does not have its codomain. So let's talk about function arithmetic. Let's say f1 of x is 2x, f2 of x is x square. f1 plus f2, we are going to add the two functions. f1 plus f2 of x is f1 of x plus f2 of x is direct addition, 2x plus x square. Whereas when you multiply f1 times f2, f1 times f2 of x is f1 times f2, that is 2x times x square, that is 2x cube. And more on the function, we have different types of function which I told you before, and the first one is the one-to-one function. A function is one-to-one if each element in codomain has a unique preimage, meaning no two values map to same result. So that's the main idea of one-to-one function. Let's see some example of one-to-one function. Here it is. As you can see, every part has a unique preimage. Every codomain has a unique preimage. Whereas in this case, E and O both are mapped with the codomain 2. So that is not a one-to-one function. Yeah, that's what. So generally speaking, the one-to-one function is injective in its synonymous with one-to-one. A function is simply injective, or a function is an injection if it is one-to-one. So you can note there can be unused element in codomain that is allowed in a one-to-one function, but as far as the mapping is concerned, they should be clearly mapped not to multiple element in the domain, whereas only one element, single element. The next type of function is called onto function. This onto function, a function is onto if each element in codomain is an image of some preimage, meaning all elements in the right are mapped. So let's see here, all the elements in the right are mapped. It is not considering whether it is mapped to more than one element in the domain or not, but still, for example, here I and O both are mapped to 2, but it's still an onto function because all the element 1, 2, 3, 4 all are mapped to some element in the codomain. So that's the objective here. That is called onto function. So here is a function that is not an onto function because you can see 3 and 4 are not mapped to any elements in the domain. Yes, this onto function is an surjunction. Then we call, if a function is surjective or surjunction is called an onto function. So here we can note that there can be a multiply used element in codomain. As I mentioned before, here I and O both are using the codomain element 2. Onto versus one-to-one, or the functions, or let's see some examples and check whether all these functions, onto function or one-to function, one-to-one function, or both or either. How about this one? You can see, of course, definitely 2 is not mapped to any element there. So this is one-to-one function, not onto function. because all other elements are clearly mapped. How about this one? A and D. Yes, you could definitely say that this is an onto function, not one-to-one function. How about this one? Yes, you would clearly see that both one-to-one and onto function would be applied to this. And here it comes another one where again you can see that this is neither one-to-one nor onto function. How about this one? It is not a valid function. Let's see some more information about this bijunction. Consider a function that is both one-to-one and onto. So here is a statement where we have a function is one-to-one correspondence or bijunction. So which means that all elements of a domain is mapped to an element in the codomain. So the identity function, a function such that the image and pre-image are always equal. So there might be some cases, for example, f of x is 1 times x, f of x is x plus 0. So the domain and codomain must be the same. So as you can see, 1 times x is still x and x plus 0 is still x. So they are kind of almost the same. So that's an identity function. And let's talk about inverse function. Anyway, we are going to dwell on inverse function for a while. So let's consider some basics of this inverse function. Let f of x equals 2 times x, and you have two things here, domain and codomain. Let's say R is mapped to R, the real part is mapped to the real part, and when you map it back or when you go back, we call the f inverse as f is mapping out to R, and f inverse is inverse function of the whole thing. So f inverse is x by 2. So here we have 4.3 from this domain is mapped to 8.6 in the codomain, that is 2 times x. And when you go back, or when you take inverse of this 8.6, eventually we are dividing by 2. Let's see more on this inverse function. Let's define this inverse function and let's examine this whole part. So here a function is given. What if f inverse of 2 not onto function? So that's a question to think about. And what if f inverse of 2 not one-to-one function? Yes, that is not one-to-one function definitely, because a and d both are mapped with 2. An inverse function can only be defined on a bijunction. So which means that it cannot be defined on a function in which two elements from the domain mapped to this one element on codomain. So in that case it doesn't work. It works only for bijjunctions or bijective. So one-to-one mapping is essential in this part. Next comes the composition of function. So this composition of function is represented by a small circle, as you can see here, f, that circle, and g of x, which means f composite of g. F of g of x, that can be stated as f of g of x. This f composite of g of x is equal to f of g of x. Well, let's see here, f of x is 2x plus 3 and g of x is 3x plus 2. Now g of 1 is yielding the result phi. F of phi yields the result 13. So as you can clearly see how this applies, thus f composite of g of 1 equals f of g of 1. So when you have g of 1, it gives us the result phi, and when you have the phi applied for the function f of x, it gives the results 13. Can you get this point? Yeah, it's quite straightforward. As you can see, the g of 1 yields us the result phi, and you are putting this f of phi there in 2x plus 3. So that gives you the result 13. So which means that this f of g of x means that initially you are performing the function that is inside. Initially we perform the g function first, and after performing the g function you use that as the x value for f, and then we apply for the function f. It's as if a function inside a function, a composite. That's why we call it as a composite function. So here's more information on this. Let's say we have 3 domains here. So first I am mapping A to B by means of G. Then I am mapping B to C with the function f. Let's say A is mapped to B. The element A in A is mapped to the element in B, so that we call g of A. Then this g of A is mapped to an element in C, that is f of g of A. In other words, if you want to map this element A in this domain A to the element in C, we would call f composite of G. That's the whole principle behind this composite function. Let's see. We could call that f composite of G. This f, the circle, and G, we call it as f composite of G. Now let's think about this example that we just seen. Let's say here again the same principle. Real numbers, all domain are in real numbers. So we have G that maps R to R, and f that maps, again this is the last R to R. So one is mapped to the element in the next domain, where we have g of 1 gives us phi, and then again this phi is mapped to the another element that gives us the result 13. So that is f of phi that gives us the result 13, which is eventually f of g of 1, that is 13. In other words, we can simply call it as f composite of g of 1 that gives us the result 14, or just f composite of g. Okay, let's see further. F of g of x equals 2 times 3 plus 2 plus 3, that is 6x plus 7. Okay, composition of functions. Does f of g of x equals g of f of x? Let's see. Let's take f of x is 2x plus 3 and g of x is 3x plus 2. So f of g of x, that is 2 times 3x plus 2 plus 3 equals 6x plus 7. So g of f of x is 3 times 2x plus 3 plus 2, that is 6x plus 11. Here it is. So they are not equal. As the function composition is not commutative. That's one of the important observations. So as we look in forward, this is a mathematical form of functions that we talk about. So in programming terms, they are quite different. So don't get confused as you do your programming functions. They are quite different from the functions that we are learned here. Let's represent these elements in graphs and see how it looks like. F of x is 2x plus 1. Let's plot x f of x. Say you have x is 1. So in that case, you will get f of x is 3 because 2x plus 1 is, that gives us 3. What if x is, say, x is 2? When x is 2, f of x becomes, yes, 2 times 2 is 4 plus 1, that is 5. Right, f of x is 5. So there it comes, another one. Likewise, if you want to plot x for various elements of x, you can try to plot it. Here it is. You are getting a linear function. F of x is quite linear. Likewise, you can also perform various other things by means of functions. Here we have plotted f of x. There are more useful things that gives us more information about this function. The first part is the floor. So as you can see here, the x is represented between the two, could you call it as the floor, because it is as if like pointing towards the bottom of x. So let's call it as floor of x. So this means takes the greatest integer less than or equal to the number. So let's say another thing that is opposite of this floor is the ceiling, because as you could see, the ceiling is just above our head, so it's as if is above the x. So ceiling makes or means it takes the lowest integer greater than or equal to the number. So let's say here round of x equals floor x plus 0.5. So let's take it out. So before we are going into this part, let's see some examples of floor, ceiling and rounding off. Okay, here is some of the sample examples of floor and ceiling. Let's try to find these values. How about 1.1? Yes, if you take the floor value, as per the definition, you are going to get the greatest integer less than, right? Less than or equal to the number. So the greatest value that's less than or equal to the number is 1 for 1.1. How about for the ceiling? For the ceiling you get 2, because ceiling has to be the lowest integer greater than or equal to the number. So for 1.1, the greatest number would be 2. Again, it's interesting because minus 0.1, we want to get the floor, we get minus 1, and for the same we get 0, and that's for the ceiling. And ceiling of 2.99 is going to be 3, and ceiling of minus 2.9 is going to be minus 2, because that's in negative terms. And this is interesting. The floor of half plus the ceiling of half is inside the floor. So why not try to examine what happens initially? You have to do the things inside, right? So try to find what is the ceiling of half first inside, that is 0.5, and then you could see what happens here. 0.5, that becomes 1. So 1 plus 1 by 2, that's 3 by 2. That's again, you're going to take the floor of that, that is going to be 1. So likewise, you can perform these values as well. That becomes 0, 1 and 1 by 2, that's 3 by 2. So again, the whole ceiling is 2. Ceiling and floor properties, let n be an integer here, and you are trying to see the floor of n if and only if n is less than or equal to n, x, and x is less than or equal to n plus 1. For the ceiling, for x equals n, if and only if n minus 1 is less than x less than or equal to n. So that's from the actual definition of floor and ceiling. Again, the ceiling, here is floor of x equals n if and only if x minus 1 is less than n less than or equal to x. In terms of ceiling of x equals n if and only if x is less than or equal to n less than x plus 1. X minus 1 is less than this floor value of x less than or equal to x less than or equal to the ceiling of x less than x plus 1. Anyway, if you could give an example and check it out, you will be finding the actual definition is correct, because these are some of the properties. So floor value of minus x equals the minus of ceiling value. Again, the minus x of the ceiling equals minus of the floor x. The floor value of x plus n equals floor value of x plus n. The ceiling of x plus n equals the ceiling of x plus n. So here's the property proof that you have. We have to prove here x plus n equals, or the x plus n floor equals x floor of x plus n. So where n is an integer, so we'll use the rule here as we have seen earlier, 1a. So 1a, you could see here, this rule can be used, where floor of x equals n if and only if n is less than or equal to x less than n plus 1. So you can go for the direct proof, where let's say the ceiling of this floor of x, let m equal to floor of x, so m is less than or equal to x less than m plus 1. That's by the rule that we had. Add n to both sides, so m plus n is less than or equal to x plus n less than m plus n plus 1. Now we are using another rule of this floor, where we have m plus n equals the floor of x plus n. Since m equals the floor of x, m plus n equals is also equals floor of x plus n. So by this we could say that the floor of x plus n equals m plus n, that equals the floor of x plus n. So eventually that's what we are asked to prove. So this is the proof of that ceiling floor properties. Factorial. Let's define some information about factorial. In fact, we have already discussed this factorial in a different lecture. So anyway, we know the definitions, and we know factorial is defined by n factorial. It can be written as n times n minus 1 times n minus 2 times so on till 2 times 1. So we could say that 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, that's 720. So likewise you can consider any value for the value of n. And this is a note for you, as 0 factorial is defined to be equal to 1, and if in fact we have some proofs to show that, but here we are not going to deal with it. Proving function problems. So let f be a function from a to b, and s and t be a subset of a. So we are asked to show function of s union t equals function of x union function of t, and the other one is function of s intersection of t equals, or not equals, it's a element or a subset of f of the function of s intersection of function of t. So this is general definition of function. Yes, we deal with subset and other criteria with regards to functions. So f of s union t equals f of s union f of t. So we will show that each side is a subset of the other. So for two cases, like we have s union t, that is f of s union t is a subset of f of s union f of t. So for that, let's say b is an element of f of s union t. So thus b equals f of a for some a is an element of s union t. So we have this element a, and then either a is an element of s, in which case b is an element of f of s. Again, remember the function property. Or a is an element of t, in which case b is an element of f of t. So thus b is an element of f of s union f of t. So we have defined this to be either element of s or element of t, but in case in this example we have tried to prove this case f of s union t is a subset of f of s union f of t. So individually we tested it for function s and for function t. Initially we assumed that b is an element of this whole function f of s union t, in which case initially we also saw that b equals f of a for some element a that is a part of s union t. So with that background, we proved that b is an element of f of s union f of t. So we have to show again this part, the second one, f of s union f of t is a subset of f of s union t. The second one, we have to prove it. So let's say b is an element of f of s union f of t. We are following the same idea that we have used before, the same way, similar step, and then either b is an element of f of s or b is an element of f of t or both. So we will say that thus b equals f of a, or some a is an element of s or some a is an element of t. So we can see that there is an element a that is a part of s or part of t. In either case, b equals f of a for some a which is an element of s union t, definitely, because a is already either part of s or part of t. So here is another one, proving function problems, like s intersection of t is an subset of f of s intersection of f of t. why don't you try this out? Let me just show you like these values. You can check it out. So the same principle, we are still following the same idea. We are taking that B is an element of S, f of S intersection C, and then B equals f of A for some element A which is in S intersection T. Similar approach to the one we have seen earlier. So this implies that A is an element of S and A is an element of T, because A is an element of S intersection T. In that case, it has to be part of both. Thus, B is an element of f of S and B is an element of f of T. Therefore, B is an element of f of S intersection f of T. So here is more on this invertible function. Let f be an invertible function from y to z and g be an invertible function from x to y. So we have to show the inverse of f composite of g. So f composite of g inverse is g inverse composite f inverse. So here is the place where we can prove. Thus we want to show that f composite of g inverse composite of f inverse of z equals z for all z is an element of z and x is an element of x. So again, this g inverse of f inverse, g inverse composite f inverse in composite of f composite of g, the whole thing times x equals x. So this is what we have to prove. So we have taken it, and f composite of g times g inverse composite of f inverse. So we are talking about this part here. So there we are just taking out this brackets and bringing this z inside. As you bring in the z inside, this f composite of g times g inverse. Initially you have f inverse of z is there, and then you are bringing in again f of g inverse of f inverse of z. So then you are taking this whole part as f inverse of z. The whole thing is taken to be f inverse of z, and f inverse of z, in fact the whole thing is a function, so that is z. So this is how we proved this part. The same thing can be proved for the other part as well. In fact, for proving these statements, I want to present you another lecture on, especially on the inverse functions, and where we are going to solve some example problems to show and prove how these functions can be solved. By here, what we have seen is just kind of theoretical way to show how these composite functions can be evaluated, but in the next lecture I will show you some examples to show how these can be evaluated. Well, today we have learned a lot about this function, and I am looking forward to see you in the next lecture. Until then, goodbye.